Today I wanna talk about homomorphic matrix computation and its application to neural network, and it's a joint work with Xiaoxin Jiang and Christine Lauder and Yongsu Song. In homomorphic encryption system, the encryption function is defined as a algebra structure preserving map between message space and ciphertext, so we can evaluate any arithmetic circuit consisting of addition and multiplications over on the encrypted data without decryption. And it's very attractive for a secure outsourcing scenario, so data owner can delegate their data and computation to an untrusted server, and we only need one-time encryption before computation, like before evaluation, and we don't need more interaction after the encryption from the data owner after encryption step. And the most important advantage is that it's secure against the attack by the quantum computer. So many people are very interested in homomorphic encryption, and the first concept was suggested at 1978 by Rivest et al. And on 2009, Gentry suggested the first lattice-based secure fully homomorphic encryption. And then the next year, DGHB suggested integer-based homomorphic encryption scheme. But they are still, they were not still practical to use. And between 2012 and 15, they are suggested a LW or ring LW variant, based homomorphic encryption scheme with several optimization techniques. So it which enables an efficient implementation. So, and after that, many homomorphic encryption scheme suggested with support various functionality. For example, CKKS support the real number arithmetic on encrypted data, and CGGI is proposed a very fast bootstrapping method on. There are several public HE library such as HElib and SEAL and HEA, TFH, Palisade, and NFlib, and so on. And until now, we are focusing on the efficiency of the basic operations of homomorphic encryption. For example, the HE community have a regular standardization meeting and to discuss about these kinds of things, and and in the past few years, there is a competition to apply the homomorphic encryption to the biomedical research. It's like a challenge. So now it's time to think about what we can do using homomorphic encryption and how we can apply it to the real world problems. And so now people are starting the research about the advanced HE tools and their usability. And as one of the starting points, in this paper we suggested a practical solution to encrypt a matrix and perform the arithmetic on the encrypted matrices. Before I start, let's take a look at the functionality of HE schemes. Some ring LW based scheme supports like packed multiple messages in a single ciphertext, so just call the vector encryption, and we can perform the perform the parallel computation on this vector. So, for example, we support component-wise addition on the vector and multiplication, and as well as scalar multiplications. And in addition, we support rotation on the vector. And actually, homomorphic multiplication and rotations are expensive among the operations. So from now on, I will just count these operations for the complexity analysis. And it definitely supports this kind of composition of basic operations such as permutation and linear transformation. There are several research about how to perform matrix operations homomorphically. Suppose that we are given d-dimensional matrix, square matrix, and the very naive method is just to use a single ciphertext for encrypt each entry of matrix. So, and then perform just a matrix algorithm in parallel. Then in that case, we need this square ciphertext to represent all the matrix components. And if you apply the fast matrix multiplication algorithm, then the complexity is around big O d to the 2.37. And on 2014, Halevi and Soup suggested a new method to multiply between matrix and vector. And matrix multiplication is kind of a series of these operations. So we just apply this method, but their approach is to encrypt each row or each column or each diagonal into a single ciphertext. So we need the number of ciphertexts to represent a single matrix, and we need to repeat d times for cover the full matrix multiplication. So the complexity is big O d square. And in our method, we encrypt a matrix in a single ciphertext, and we suggest a method to express the matrix multiplication by combining very HC-friendly operations on packed ciphertext. And we could achieve so we could achieve a big O d complexity. And the very main attractive is that our method is very generic in the sense that our method can be applied to any ring LWE scheme, homomorphic encryption scheme. So now let me introduce our idea. We first identify d square matrix to a d-dimensional vector using a row ordering encoding map. So as you see, as seen in this picture, addition is very easy. Just perform component-wise addition. And you can also think about row or column shifting permutation. For example, row shifting by for easy understanding, I take 3 by 3 matrix. Then row shifting by one row is corresponding to the left rotation by 3 in a vector sense. So in that sense, row shifting is just one left rotation, so just big O1 complexity. And column shifting is kind of a little complicated, but we can obtain by combine the rotation and some scalar multiplication by some by some constant masking vector with 0 and 1 field. And but the previous operations are that's free, just addition or just rotation. But in this case, the column shifting or permutation requires depth 1 because depth 1 of scalar multiplication. Now let's think about how to represent matrix multiplication in H-friendly sense. As you've seen in the right side, if we are given the dimensional matrix given, then the matrix product can be expressed as a 2 times the permuted matrices, as you see. So, for example, in this, if we just consider 3 times 3 matrix, then the matrix product can be expressed as a 6 permuted matrices, and the first the A sub I matrix comes from A, and B sub I matrices come from B. Let's think about it a little bit more. If we perform the inner product of the first row of A and the first column of B, then we have the A product B is 1 1. So, and in the sense of in our equation, the component of the first row of A are spreaded on the same position of the AI, and in the case of B, the component of the first column of B are spreaded in the same places, but on the B sub I. So after generating these kinds of permuted matrices, we just need to perform element-wise multiplication and addition. So that's all. Now let's consider how to generate this a little complicated permuted matrices. In the first step, we consider how to generate A0. We first represent the input matrix and the output matrix as the corresponding vectors using our encoding map. Then the operation is just can be seen as the linear transformation between very large matrix and the input matrix, the input vector. Then we have the we obtain the output vector, and we need to think about how to evaluate these operations homomorphically. In this sense, we apply Halevi and Soup approach. It means that we handle this large matrix as diagonal vectors. So this operation can be expressed like a multiplication and addition between the diagonal vectors of the large matrix and some rotated input vectors. And fortunately, most of diagonal vectors are 0, and some small diagonal vectors only non-zero. And the number is, we count the number, and the number is 2 times d plus 1 for the dimensional matrix. So we can represent this linear transformation as a 2 times d plus 1 in scalar multiplication and addition. And the next step, B0 is can be obtained very similar way. with big O complexity. And A sub I can be obtained by the column shifting and a column shifting by I column. And as I mentioned before, the complexity is big O1 for each one. And the next step is to generate B sub I, and B sub I can be obtained by just row shifting by I rows. So it's just a rotation. So the complexity is big O1 for each one. And the final step is just perform element-wise multiplication and aggregation. So the complexity is big O-D. So in terms of depths, it requires two depths of scalar multiplications and one more depth for homomorphic multiplication, and the total depth is big O-D homomorphic operations. And we also suggest more advanced matrix operations, such that matrix transformation and multiplication between non-square matrices. And we also think about the flexibility in uses. What I mean that when the number of plaintext slot is larger than d square, then we encrypt several matrices in a single ciphertext. So, and then just perform the parallel computation. For example, if we are given 4 different metrics, then we can embed into a single ciphertext in a consecutive way. And if the number of plaintext slots is smaller than d square, then we split large matrix into multiple ciphertexts and do the blockwise computation. Here is our experiment result. The second column means the number of the matrix sizes in parallel. So for the dimension 4 cases, we can just encrypt one matrix, or at most we can encrypt 2 to the 8 matrices in parallel. And the total time is exactly the same, but we encrypt more matrix size, then the relative is exactly divided by the number of the throughput. And the dimension for the large case, dimension 16.4, it took about around 9 seconds. And we use the Heian library, which implement CKKS scheme. If we use a little bit faster version of CKKS, then we check that the performance can be faster 6 times. But we didn't report anywhere. And we applied our matrix mechanism to neural networks. Our scenario, our goal is to predict the encrypt data using the encrypt trained model. Our motivation is that maybe data owner may feel uncomfortable when they upload their data to third party platform, and model owner also wants to safeguard their critical model parameter. So in our scenario, data owner encrypt their data, and model owner also encrypt their data and upload to the cloud, and cloud makes some prediction on encrypted date and encrypted model and send to the certified authority. And we apply our matrix multiplication mechanism to the convolution neural network to classify multiple images of MNIST data. Actually, we encrypt we encrypt 64 messages in parallel. And yeah, the data owner encrypts the image data, and the model owner encrypts the corresponding kernels and the weights of the networks. And we consider the neural networks consist of the one convolution layer and two fully connected layers. And for simplicity, we use the scalar activation function. And the total running time, the total evaluation time is around 28 seconds. It means that it took about 0.45 milliseconds to classify a single image. And there are some preliminary results for the encrypted prediction phase using homomorphic encryption or MPC. If we compare the techniques, the results based on HE, then it seems a little comparable, even though we thought our scenario is a little more secure, because all the techniques assume that the neural network model is not encrypted. Thank you for your attention, and it's my pleasure to take a question.